So welcome on in. Today is Friday, so after today, it will be the end of our third week dealing with assembly. And that means you only have 2 more weeks. Next week is your exam 2, and then the week following that on the Friday is exam 3. I do believe we lose Monday the 5th for Independence Day weekend, so you will also have that day off. So we actually have 4 days to cover over MIPS. So we may or may not be able to fit in an assignment, but more than likely I will have maybe a coding section in the exam, in your final exam, for MIPS, regardless whether or not we'll have an assignment that week. Okay, so Flavorance Day is going well so far. So did this itinerary. Today is going to be a relatively short lecture topic. We're just going to wrap up week 3's syllabus. And then I did notice there were some questions being thrown around last night about homework 4B, so I thought it might be a good example to kind of revisit that. I think I made the homework assignment a little bit more difficult than intended, but it shouldn't be too bad because you should all have the tools to do homework 4B. So before we maybe talk about questions about homework, let's go ahead and finish the lecture topic for today. Okay, so we're going to be talking about the tool chain and a little bit more about how to link multiple source files or object files. So let's go ahead and get started on that. Okay, so regarding the tool chain, and multiple files. All files. So all this time, we've basically been working with one main file, but obviously programming isn't that simple. Sometimes we'll have a team of developers. Each one may be responsible for writing a few functions, and then some of us will maybe write the main function that will invoke the other functions, right? So to do that in assembly, it's quite similar to higher level languages. But first, maybe let's go ahead and talk about some prerequisites. So I don't know if it's helpful or if you guys like it when I write out full definitions. But if it does help you, let me know and I'll continue doing it. But if you don't really need me to write it down, then that's also fine. So let's say if a function is called from a source file. Good for notes. I like it. It's helpful. Okay, yeah. So I'll keep that in mind, and I'll try to write more things out, as well as maybe providing some more diagrams to kind of help the flow of the notes. So if a function is called from the source file and it's not declared, do apologize if my penmanship isn't the best on the tablet. Current source file. Little error. So basically, if you don't, your function is not in the main file where the program is run from, then it would usually generate an error. And this goes the same, so same or similar for variables that aren't declared in the main or the source file that it's residing in, not in source file. Okay. So to circumvent this, we need an extra instruction to tell the assembler that it should be looking for the function outside the source. So let's see. This is how to inform the assembler by invoking the following instruction. So you will use the keyword extern for indicating that an external argument is being passed in. So extern will be a symbol name. And usually this will be a function name. So symbol name here can be a name of a function. Or variable located in another source file. Okay, so while we do say you can call a variable from a different source file, we can also say in general using global variables is poor practice. So usually frowned upon, unless it's a very trivial thing like system call operands. So you should normally just use argument transmission to pass things to different functions. Okay, so for whatever reason your global gets changed, then all the code that relies on that will also be affected. There's an abundance of different reasons why using globals is usually what we consider poor practice. Okay, so if you usually the symbol name will normally pertain to just the function name because we're good programmers. Okay, so if for instance maybe let's see, maybe I'll start a no, I won't start anyone. Let's just continue on this. So quick example. So maybe in my section .data, so this will be my main file. So this will be maybe my main.asm. Okay. Here maybe I have my system codes, right? So syscall codes defined or standard constants. Maybe I declare some variables in data. Okay. Then maybe I have my bxs section where I declare some more variables, declare uninit variables. So non-initialized variables. And then we have our section, oh, before that. So let's go ahead and, so here's section dot text, not data, text. Okay. So here is where my here's where my main would usually start. So the start, the underscore start basically tells the linker where the first RIP should point to, right? So where the program starts. But here, let's go ahead and make this in red, is where you would put all your externs. So extern, for instance, maybe in this program, we'll call something called stats. So our function name is called stats. So stats is a function name. Okay, so that's kind of where you would put it. And maybe we'll do some code for good practice on getting used to the standard calling convention. So maybe all this main program does is it invokes stats, and it will pass in A, B, C, D, E, F, G, H. Let's assume these are 32-bit ints. Okay, so here's an example of the SCC. So, Let's see. C says, okay, well, I know my first 6 arguments. I had some questions about why we do certain things following the standard calling convention. So remember the first 6 arguments, so A through F, are going to belong, we're going to say move EDI. Remember the first 6 arguments go into EDI, ESI, or the RSI, RDI, or RDI, RSI, RDX, RCX, R8, R9 registers. But we notice that these are 32-bit variables, so we are only going to use the later 32 bits of our registers. And I'll just do them in order. So D word A. So of course we have the same things for ESI and B respectively, EDX and C, ECX and D, R8D and E, R9D and F. So those are going to be your first 6 arguments. So notice that we have 2 more arguments. Maybe I'll do these in a different color to kind of coordinate that a little bit better. So arguments 7, 8 need to be put on the stack in reverse order. So again, remember that on the stack, we need to utilize 64-bit operands to push them up by. So what I can do is first store, let's say, into EAX, the value of H. So D word H. Okay. And then I can push RAX, which is my 64-bit, right? So here, store 32-bit data in A register, and then push entire 64-bit A register. So essentially, this right here pushes H on the stack, right? H and maybe 32 bits in front of H, but when we extract it as a 32-bit variable, it doesn't matter. And I'm just going to write 1 more or 2 more lines of code for the other one. So move, and I can overwrite EAX here so if I don't want to use another register. I can overwrite it with G, and then push RAX again. So now so this code essentially says that G is on the stack and it's pushed after H, right? So in reverse order. Okay. My standard calling convention says now that I can call my function. So call stats, right? So I assigned all my variables. And then because I have 2 arguments on the stack, right? So maybe I'll put this into blue again. Because I have 2 arguments on the stack, I have to add or change my RSP by the number of bytes. So be 8 bytes because each item on the stack is 8 bytes and times 2 arguments on the stack. And that's what gets our 16, right? So visually, what this will look like is maybe my stack pointer right now on function call is here. It doesn't matter if I have stuff on the stack before that. Is it good practice to XOR RAX before using the register again? So XOR RAX basically zeroes out the register. Let me just, maybe we could talk about that really quickly. So XOR RAX will zero out the register, right? Because exclusive OR basically says put a 1 wherever 1 is. So XOR says 1 if they're both different, right? So both different. Or 0 if both same, right? But because RAX and RAX are both the same, then it will just zero out the entire register. So you could do that. In this case, it's not necessary because I'm overwriting only the 32 bits that I previously stored. So it's fine. There's no need. You could do this extra bit if you want to be pedantic, and while it's not redundant, it could be good practice, but it's not necessary. Okay, so the first time we pushed RAX, we have the contents of H in here, and then the contents of G was pushed on after that. So this is before my function is called. My function call tells me to push RIP onto the stack and then go to the function, right? So this is what the stack would look like when I go to my function. When I leave my function, when I get the return call back, right, I know that RIP will be popped back onto the RIP register, or whatever this value is, or address. Is going to be into my RIP, which will point back to here, right? But if you notice, when I pop this, so RSP is already updated. So RP is now, or RSP is now here, right? Because I have nothing on the stack anymore. This is gone, right? But you'll notice that earlier, before my function call, this is RSP before SEC function call, right? So before I used any standard calling conventions to put arguments on a stack, this is where I should be pointing at, right? To the contents of whatever the stack is here. But you'll notice that I am offsetted by 16 bytes because I stored these stack-based arguments. But you'll notice when I push them, I never pop them anywhere afterwards, which is why they're still on this stack. So in order to get back to my original starting point, I have to do this command to add RSP by 16. Of course, you can just push, or you can pop two things off the stack, and that will be fine. But if you have, say, 50 items you pushed onto the stack, you would have to pop 50 times, and that seems a little bit that's prone to errors a lot more, right? If you don't count to 50 correctly. So instead, if we can mathematically just update RSP, that's a lot easier to do. Even though it will overwrite and clear the items on the stack, when you push something on, these contents will be overwritten. Okay, so that's why we need this. This is a very important step when we do our standard calling convention, right? Remember, there's three things that happen. One of them is that the caller routine must update the stack pointer back to its original starting position before the function, the standard calling convention for the function was invoked. Okay, so that's just a quick recap on standard calling convention. This is a very, very important concept that you must know. If you don't know anything else after this assembly class, and if you just know this, that is good enough. Well, not really, but it's just really important. So make sure you fully understand the standard calling convention, because that provides a lot of portability for different codes and functions. It is what everyone goes by when dealing with object-oriented programming. Okay, so let me go ahead and maybe we can do some code on the second source file. So let's say we terminated that main file, and then here, let's go ahead and maybe code our function source code. So that was main. Now let's go function source code. Okay. So same thing, the body of the code, or the program, right? The anatomy of the program is going to be the same. You'll have a section data, but you should not use any declarations here. Declarations, right? So don't define any variables here if it is a function source code. So let's go ahead and maybe talk about the text, because that's where your code will go in. Okay, so maybe in this text, right? we'll say that this is the arg. So what do we say? It was global stats, right? So stats and the stats label, right? And then maybe as good protocol is maybe you'll explain what this function does. So documentation. So maybe talk about what this function does, and maybe list the arguments that are passed. So args passed, say something like number one, we expect it to be an RDI. So remember, we can have floats being passed as well. So it might be important to whoever is trying to call your function to know exactly what arguments to pass in which registers. So contains int a, right? And then you'd say RD or RSI, same thing, right? B. And you list them. Maybe you'll also say to stack based args, G and H, right? So that way, whoever's calling your function, once they read the documentation, can understand, oh, this is what I need to do to set up my standard calling convention before I call the function itself, right? So it'll tell them that I need to save A into RDI, I need to save B into RSI, and then I need to save these two on the stack, right? Okay. And then maybe the next one will also say returns value in RAX, right? And then you'll maybe specify what that value is, and then you code your function, right? So maybe we won't code what the function does, but we'll at least grab the variables off the stack so that you can see how the standard calling convention like that works. So first things first, maybe it would be a good idea to push RBP because we have stack-based variables or stack dynamic variables. Maybe we want to move the current RSP into RBP. So let's go ahead and maybe draw the current memory frame that we're working with, right, from earlier. So here's the contents of H was pushed in first, then G, then RIP. So right now on function call, this is on call. This is everything that happened, right? RSP is here. Then we push in RBP, right? So, and then we set RBP equal to the current RSP, which is here. And now we can declare any stack dynamic locals. So maybe I'll use blue for this. And I can say, maybe I want to allocate some space. So maybe I would say sub RSP by however many bytes, right? So in this case, maybe I'll set aside 8 bytes, right? So this is saying set 8 bytes for stack dynamic locals. So 8 bytes, okay, so I will set 8 bytes here. And this is reserved for SDL, so this is RSP minus 8 from this RSP, right? So from this RSP to this RSP is 8, and this is the current RSP. So, and this is also equivalent to RBP minus 8 from this RBP, right? Okay. And then maybe I do some code here, right? If I wanted to access and store H and G, I can say move. Maybe I'll use a different color. Let's go ahead and use red. So if I wanted to save my variable, so like move, let's say dword, or maybe we don't use dword, maybe just use a register instead. So maybe I want to store EAX as G, right? So I would have to say dword RBP minus, or sorry, plus 16. All right. So if this is my current RBP right here, This is RBP plus 8, which will give me the RIP pointer, or the RIP address. And then this is RBP plus 16. Remember that each item on the stack that gets pushed is 8 bytes, or 64 bits. If I wanted to reach to H, I would need RBP plus 24. Okay, so maybe I do move. Let's say if I wanted to use EBX, I would also maybe do something like this before that. I would save the value of RBX because RBX is a preserved register. So maybe I'll do push RBX, right? So RBX is here. But let's say now I want to use EBX. So EBX dword RBP plus 24. So this one stores EAX equal to A, G, and this one stores EBX equal to H. Okay, so remember the reference here. Okay. Then maybe I'll do some code. Doesn't matter what my function does, but to wrap up the standard calling convention, we need to say, I'll also do this part in blue. So whatever I did to the stack, right? So notice here, I push something, I move RSP, and I push something, right? I have to make sure that I undo all of those things. So what I have to do is first, do it in reverse order, right? So if this one was third, I have to do this one first, then do this second, then do this third. So I would have to pop RBX. I would have to add RSP by 16, right? So once I popped RBX, my stack pointer is here. And remember, I allocated, maybe not 16, 8, sorry. I allocated 8 bytes for these stack dynamic locals. So this right here clears the SDLs on the stack. Remember that the stack dynamic locals don't really are not saved. Otherwise, you'll run out of available memory. And then I need to pop RBP. Sub RSP in bytes, not bits. Yes, sub RSP in bytes, not bits. Because remember, the memory allocation is byte addressable, which means it's in bytes. So each one of these actually is divided into 8 bytes. Except when we push and pop, we're doing it by 8 bytes. That's why it's has to be in that structure. Okay, and then my return function, right? So once I pop my RBP, I'm back at the RIP right here. I pop that, and now my RSP should end up here when I go back to my function caller, right? So my function caller is here, and I am currently back at this pink line right here, which is why we need to add the RSP back 16 to update where my stack pointer should be before the function was called. So everything I do, I have to undo basically. And that's more or less the standard calling convention. Okay. The last thing I want to talk about in regards to this is we kind of see how to code a separate source file, but how do we link them and assemble them so that we can use them? Okay, well, that's fairly simple. So by now you should already be familiar with how to assemble a simple program, right? So of course we have the YASM -G dwarf2. These are just all formatting stuff. So -F, elf. YASM is the assembler, and these are all just formatting. And then we have the main.asm, right? Dash L, and then main.lst. Okay, so this one right here assembles the first the main program. So you'll have to do this for any source program that you provide. So I'm just gonna do this, so I don't have to rewrite that part. And then we do, maybe this is the stats.asm dash L stats.lst. Okay, so now I should have two object files that are generated from these two instructions to my assembler. And then to top it off, I just have to call my linker and link my object files main.o and stats.o. And then I should get a program that links all these functions together, and then I can just call that file or that executable. One useful thing that might be helpful is on the debugger, there are these things called step and next, and they should help you traverse through parts of the function code that's not in the main executable or the main object file. So try to utilize these if you are ever using functions that are not inside your main file. And then lastly, maybe we'll talk about how to link higher level language programs. So if you want to write code in C++, if you want to have a function to use in the standard library or whatever, all we need to do is just compile it, right, with G++. So maybe this might be a compiling code that you might put in. So maybe your main function is written in C++. Okay, so this should generate the object file. You're gonna use the same code. We'll just call this up. So the same code here. That will create the object file for your function that's written in assembly. And then you can call G++ -o, your main.o, which is your main object file, and then your external function source file, right? Depending whether or not or what operating system you're using. So I think Ubuntu 18, you might need to add in an extra command called nopy. So this is maybe for Ubuntu 18.0. But a few more command line arguments. If it doesn't work for you, you might need to troubleshoot based off of your operating system. If you wanted to use C code instead of C++ code, just change the G++ to GCC and anything, and just compile it as you would a C code. So that about wraps it up for our lecture topic on the linker and the assembler. And hopefully the little standard calling convention review was helpful. So are there any questions about either the SCC or the linking and the assembler? So someone asks, does move RSP RBP do the same thing as add RSP 8? So let's go ahead and look at what we did. So maybe I'll use green to kind of document what we're doing. So maybe you're saying in this line right here. This line right here, you're saying, is it equivalent to move RSP RBP. Okay, so if we moved it here, yeah, you could do that. It should be the same. Yeah, that should be the same address that you end up with, assuming you didn't edit RBP. Then yeah, this should be valid. This might be a question you can answer later, but is there extension you use to assemble this code in Visual Studio Code? No, I don't do any of my assembling or compilations on VS Code. So I wouldn't be able to answer that personally, but you can probably look stuff up online to troubleshoot that if you do want to do it on your IDE. I've just ran into a lot of weird issues compiling on IDEs or assembling on IDEs that I like doing it the command line way. But doesn't mean that you can't do it. Okay, so hopefully this isn't too new. This just allows us to kind of write functions in different source files. Obviously, our functions we write here probably can all fit in main, but in general practice, not all your functions are going to exist in a main file. So it might be important to know how to link multiple source files together. We just need the script to be updated. Yeah, but it needs to be updated every time you want to make amendments to it. So as long as you know how to do the command line code for it, it shouldn't be overly difficult. So we have a little bit of time. What I want to do is maybe address some stuff in homework 4, and then that'll be it for the lecture for today. And maybe I'll let you guys go early to try and implement your assignment 4. So what I did notice in assignment 4 is a couple of things that might be useful to know. So originally, I didn't intend for it to be as intricate as it is, but it might serve as good practice anyways. So let's kind of maybe analyze it a little bit further. So let's go ahead and pull up the template. So if you notice in the template that I declared all of these as D words, right? So remember when it comes to D words, so D words are 32-bit, right? And if we go ahead and pull up our textbook for reference, you will see that D words are in their unsigned range. So obviously, in this case, we're dealing with unsigned values because the sides of our prisms cannot be negative. So it is implied that everything we'll be doing with this one is unsigned. So we know that the maximum range for unsigned is going to be about 4 billion, right? So we know that the max that a D word can hold is roughly 4 billion. Okay. But if you look at our code here, you'll notice that maybe some of them have quite a bit of numbers. So if you multiply 2 numbers together, you might be under that 4 billion threshold, but multiplying 3 numbers together, you might exceed that. So you'll notice that these values here are assigned to be quads. But when we multiply, our solutions are going to be stored into so 32-bit multiplication, right? Will basically say if you have the instruction mul by say EBX, right? This will put my solution into EDX and EAX, right? So if for instance, the number exceeds 4 billion, then the overflow or like the most significant bits are going to be stored into EDX, and then the least significant bits in EAX. But you still need to kind of convert this into a quad to store into your variables if you want to use that. So here's a simple way to kind of go about doing that. Let's recall what the shift left instruction does, right? So if I have some number, like say 1001, right? Or let's put in some more zeros, right? If I have something like this, if I call a shift left of, let's say this is as 8 bytes, so it is or 8 bits, so this is a byte, so let's say this is in the DL register, right? If I say DL, what was that, right? And then maybe our DX register is 0, 1001, right? So this would be my DL, this is my DH, right? And they all make up the DX register. If I say shift left DX by 1, right? Then I will move this over 1 space and add a 0. But if I want to say maybe shift by 5, what happens is now I get 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and then so I've added 5 zeros here, but you'll notice that I've moved my most significant bit over to the next register in the DH register, right? So it's a little nifty trick we can kind of utilize. So if I, for instance, want my result, so my result is an EDX, EAX, right? If I want to, say, use a 64-bit register to hold this 64-bit value, right? So the upper 32 bits are here and the lower 32 bits are here, right? What I can do is maybe call a shift left RDX, right? So RDX is my 32-bit. And then I can move that by 32 bits. So 0x20 is the hex value for 32. So this is just hex for 32. But this tells me that I want to move by that many bits, so 32 bits. So if I'm at the RDX register, let's say it's zeroed out for now. Well, all the components are going to be zeroed out. So I have zeros. The first 32 bits are zeros, and then I have stuff in my EDX, right? When I shift by 32, my entire EDX register basically is sitting in the upper 32 bits of RDX. So RDX basically now has the stuff here, which was moved from EDX, and the new EDX is going to have just a bunch of zeros, right? The 32 that I filled in by shifting left. Okay. I know that my EAX contains the lower 32. This is maybe the stuff that I want to put in here, right? So all I have to do is just add or move the values of EAX into there, right? So move RDX. So, oh, maybe I don't want to do that. Maybe I just want to add RDX. And then we need to zero out the A register first if we're doing this. So make sure you zero out A register before doing this, and then you can do an add RTX by RAX. So if RAX was zeroed out, and then we have stuff again, so this is stuff, maybe we'll call it stuff 2, right? So now we have basically fit everything into RDX, right? Stuff, and then stuff 2, right? It's all fitted into RDX, and I can pass that into, say, volume, if I, for instance. So if you have overflow, that might be something useful. Could we move EDX, EAX? You can, but remember you would have to make sure there's oh yeah, that'd be an easier solution. Yeah, you can move sorry, I guess, or move EDX, EAX. That would also work, right? Because you're not messing with the upper 32 bits that you've already set, and then you're only extracting the 32 bits of EAX or the A register and putting it into the bottom 32 bits or the EDX register. So yeah, that's a good suggestion. You can do that. That should work as well. So more than one way to kind of get to the end result. Okay, so that might be helpful if you do experience overflow, which you should, at least in the last one, because if I remember correctly, this one ended up being in the quintillion, or no, not quintillions, but I don't remember. I think it was like 16 units long, so whatever that translates to. Um, I double checked it this morning, just plugged in a calculator and figured out that it should fit in. Uh, Assuming I got my units right, it should fit in a keyword. If it doesn't, then I may to adjust one of the values, but it should when I double checked. Okay, so that is how maybe you would do that problem, or convert, convert it into a quad and store it. Let's see. Alternatively, maybe you can also do something with memory manipulation. So you know where the address of each of these variables are, right? If you just don't reference, and you can specifically ask to put certain values in certain parts of those registers. So maybe you can do some addressing there. So more than one way to go about fitting values in. Let's go ahead, and then I think there was one question about printing integers. So I did have a slight oversight where I forgot to mention that when printing using the print statements, they will print strings. So the standard write will print strings. So to print the integer, we have to convert the integer into a ASCII string. And it's not too difficult, so maybe I'll go over that right now. So okay. Is it possible to get extension on this one until Monday? I still don't think that you'll need 3 days to finish it, considering that I will probably finish most of the ASCII part for you, just for a good exercise. Okay, so and I'll even do it in a function so that we can get a little bit more practice using the standard calling conventions. Okay. So the loop and stuff for calculating, I'm sure you can do that on your own. I think I've went through enough examples for that. So I'm going to assume here. So the assumption is your values are ready to be printed. Okay. So assuming that your volume, all these values are stored already, and then we're just calling a print. So what I'll do is I will invoke a function to print. And you don't have to write this as a function. I personally am going to do it as a function because there's a lot of code that's going to be recycled. So it would make sense for me to write a function. So maybe I will write a function called global print stats. and its job is to simply print the stats. So print stats. Okay, so maybe I'll say that this is a function to print integers as strings, and that means that there will be an ASCII. So let's say maybe we can document some things. So it takes in arguments. So the following arguments, maybe I want to at least pass in one, right? So I'll set it up like this for now. Maybe we'll make changes along the way. So let's say long integer, right? Value to be printed. So essentially, I want to pass in one of these values that are quads or 64-bit. Remember that my first argument is stored in RDI according to the standard calling convention. Maybe I'll use RSI. I don't know what for yet, so we'll just hold this for now. And then let's go ahead and do some stuff for standard calling convention. So maybe CC stuff would be here. So maybe we push RBP, move RBP, RSP. Okay. Let's say maybe I wanted to use some stack dynamic locals. So maybe I'll do a sub RSP. Maybe we want to set aside 64 bytes. So here we go. Set aside 64 bytes for stack dynamic locals. Hopefully you can see this. I can zoom in just a little bit. Can we put functions in the main assembly file like this and it'll work? Or do we need a separate file? You can do both. There's no reason why it shouldn't work in the same file. You just, as long as you put it under the text section. Here, I don't have to write, I don't have to do like an extern, right? So no extern print stats needed because it is inside the same function or inside the same main code, right? So any object files that, any source or object files that you need to link together, you have to reference them with the extern. Otherwise, it won't, the linker will not know, and then your assembler will cry. Okay, so where are we right now? Let's go ahead and maybe push any preserve registers. So push RBX, for instance. Push any preserve registers as part of our standard calling convention. Okay. So maybe good practice is to maybe let's say let's go ahead and say clear print stats. And then all this is we'll update anything as pertaining to the standard calling code convention. So maybe if I pushed RBX, I should pop RBX. Since I subtracted RSP, I should add RSP 64. And I pushed RBP, so I should pop RBP. So doing this now will ensure that I don't forget to do it later and run into any issues. So that's how I like to do it, and I think that's a fair way to make sure that you're on top of things. Okay, maybe now that we have all of these things set up, we can do the algorithm for converting the ASCII values. So we know that RDI contains the value, right? So maybe what I can do is save the value into RAX and RDI. So for ASCII, let me go ahead and talk about it just very briefly. So let's see. If we go to ASCII, here's the ASCII table. Let's zoom in. Hopefully you can see this, but if we look at the digits, right, 0 through 9 are right here, right? So value 48, 49, 50, 51, 52, 53, 54, 55, 56, 57 are going to be what are assigned to your 0s through 9s. So if I were to say, if I have a value 0, I want 48, right? If I have a If I have a 1, I want value 49, and so on and so forth. And you'll notice that the difference between the ASCII and the int representation is 48. So if I add my integer with 48, this will give me the ASCII representation of in string. So if I ask my machine to read what 48 is in terms of ASCII, which is what your system call is doing, it will give you 0 as the output. Okay. So if I had a number, say 1, 2, 3, 4, 5, I wanted to print in ASCII, what I would have to do is take this number, right, and then add it with 48, take this number, add it with 48, and so on and so forth, and build my string like that. And we know that this is in decimal, so to extract this value here, all we have to do is divide by 10, right? So if I take a number and divide by 10, like 1, 2, 3, 4, 5, I should get 1, 2, 3, 4 in the RAX register, and in my RDX register, get the value of 5, which is my remainder. And you'll notice that my remainder will be a number between 0 and 9, which conveniently makes sense. So instead, what I can do is say add RDX by 48 once I have the division done. And I just have to keep dividing until RAX is equal to 0. Right? So so once we get to 1, right, which is the last digit here, 1 divided by 10 is equal to 0, remainder 1, and then 1 will be stored into RDX, and 0 will be stored into EAX, and this will tell me how to terminate my loop. Okay? So if we maybe convert this into code, we can do something like this. So let's go ahead and move RBX by my divisor, so 10. So this is the value to divide by in order to isolate the digit. Okay. Maybe we move RSI to be 0, and I'll use this as an index to tell me how many digits I'm using. Okay. Let's see, maybe start my loop once I've initialized everything. So convert loop maybe. So what I want this loop to do is say convert last digit to ASCII, then store into a buffer for the stack in reverse order. So first things first, I want to maybe move RDX to 0. Since RDX can be a argument, this might be a good idea. You might want to also maybe preserve their RDX value if needed prior to this. So RDX is going to be zeroed out, or you can also think of it as sign extending, or however you want to do that. Because my value is a quad, I'm using RAX to divide, so divide RBX. So this is basically taking RDX, RAX divided by RBX, and then the remainder is a value between 0 and 9 stored in RDX. RAX is the leftover. Okay. So maybe what I can do here now is add RDX by 48, and so this value should end up in the lower 8 bits of the D register, so DL, because we know 0, even if it's 9 plus 48, we know that 8 bits is enough to represent 57. Right? So this value should end up in the lower 8 bits of my my register. Okay. So now all we have to do is to ensure that we place it in reverse order, right? Ensure that we store value in reverse order. Okay. So maybe what we can do now is store it somewhere. So let's go ahead and move. We have 1 byte of information that we want to store in DL. So RBP minus 64 plus RSI DL. Okay, so let me go ahead and switch back to a diagram maybe. So in the code, what I'm doing is, here's my stack. Maybe I have stack-based arguments, maybe I don't. But we have RIP, we have RBP, we have this, so RBP is pointed here. I set aside 64 bytes for the SDL. And so this bottom bit right here, it's what my RBP minus 64 is, right? At this time, my current RSI is equal to 0, so it shouldn't change my address. And then this is where my RSP is, right? So RSP is here because I pushed in RBX. Okay. So the code that I'm showing you here, where I said move byte RBP minus 64 plus RSI DL, is storing 1 byte, which is the ASCII value, into, let's make this a different color. Let's make this full. So I'm storing whatever the ASCII value of DL is. So maybe I'm storing 48 in here, or yeah. So maybe I'm storing 48 in there. Maybe I'm storing 49, or so forth, depending on what the integer value is. And every time I loop this, I'm going to update my RSP or RSI, right? So if RSI is 1, then I'll be at RBP minus 64 plus 1, which means I'm at the 63rd bit, right? And I'll put in my next value. And as RSI increments, I'm going to be moving up my stack. And what I can do is when I call my system write, I can pass this address in, right? And tell it to read RSI worth of, well, RSI being my index, but it tells me how many bytes to read from this buffer. Okay. So that's the approach that I will use here. Of course, you can declare your own buffer either in the BSS section or as a initialized variable, as long as you can store all the digits. There shouldn't be 64 digits, and I won't really run into the stack overflow or stack buffer overflow problem because I'm not prompting for user input. I'm able to put as many or as little information onto my buffer as possible or as I want, and no one can really touch that. So that should not be an issue in this case. So if we go back to the code, here I'm storing store ASCII value into in reverse order. So I'm moving down and up, from down to up. Okay, I can increment my RSI, so increment index, right? And my index is used as a counter for how many digits to display later. So it kind of double dips in this case. I can compare RAX to 0. So I remember RAX stores the quotient, right, when we do the division. So RAX stores the quotient. And if RX is eventually 0, that means if 0, then no more digits to convert, right? So jump not equal convert loop. That should loop me back the division and push any converted ASCII value bottom up. and then maybe we can do the print instruction. So ASCII, maybe something like this, where we say move RAX sys right, move RDI STD for standard out, and then I can move RDX RSI. Remember, RDX is how much to write by, and then the address that I want to give it. So A SI byte RBP minus 64. So I'm telling it to look at the address of where my buffer starts. That way I can print it out in that order. Okay, and then I just do a syscall. That should be it. So once it's done storing into the buffer, so here's my buffer. So I have all these values up to here maybe. So RSI is here. And then because I don't want to overwrite RSI, I can store the index or how many bytes I want into the RDX register first before overwriting RSI by this address. And then I'm able to print from that address and call my system call. And that should be my print function. And the last thing I have to do is return back to my system call or my function call. So it will take me back to here. So let's say we invoke print stats, and then maybe before that we had move RDI, or what is this? Yeah, RDI, since it's 64 bits. Keyword volume. So maybe in this case, when I called print stats, I did the volume, move RDI, keyword min volume, and then print stats, and that will more or less be able to print everything once I am done. So in this case, RSI was not used, and that's okay. So we only had a one argument function, which is fine. Sometimes you don't really know how many arguments if you're the one coding the function, unless you're given the arguments from the main ahead of time to write for. But that should more or less be the code for converting to ASCII. I might have some syntax errors. I might have forgotten some small details, but that's more or less the bulk of the code that you might want to try to use. You can do this method in an abundance of different ways. You can write your own buffer, so you can have your own array store values. So maybe you can declare a BSS, right? So ASCII array, maybe you can say DB and assign 64 bytes to store. That's probably more than you need to. And then here, instead of the address of my buffer in the stack, I can just simply say that this is equal RSI, or move RSI, the address of ASCII array or something of that equivalent. So more than one way to do this. This is more or less the algorithm to byte by byte convert the decimal, or I guess digit by digit, convert them into ASCII, store that ASCII representation back into the buffer, and then print from the buffer. Okay, so that should help you with printing out integers. So we print them as strings, and that's this is more or less the function to convert them from integers to strings. Okay. Are there any questions on the topics that we covered today, or your homework assignments? So more or less, you only really need to do the loop and then make sure you understand how the system write works. The ASCII is not too hard. It was only like 10 lines of code, maybe 15 lines of code. So it shouldn't be too bad. If you need help, always just pause the lecture recording and look at the code. But hopefully that was thorough enough for you guys to all more or less understand what you need to do to print out an integer as a string. Do we have an expected output key? No, I didn't make a key for this assignment yet. But you can just plug this into a calculator and get your answer key there. So it's not terribly hard. So if it works for the first two, chances are it works for the latter 9. It only takes like 3 seconds to maybe like go to Wolfram, then plug in, copy this, paste this. If you wanted to find volume, just plug that in. So that should be your expected output for your volume. And if you wanted surface area, you can do 2 times by, I guess it's a little bit more involved, but you'd have to multiply this and this stuff. See, that should be your surface area. Shouldn't be too bad. They should all fit into quads. So your surface area equal that, and then you would have to print the maximum. Let's say if this is the maximum, then that's what you print out as a string. You don't need to use functions, but I do strongly recommend that you do. It's good practice. And it's not too hard, right? You saw me code the entire thing basically. So the reason why I can call these like this is because they're globals that are defined here in the data section. So your function should be able to see them without having to pass them as arguments. Of course, you can just overwrite this by saying 1 or something like that, and that would be completely fine too, as long as you have the correct system call codes. So any questions on the homework? If you're really fancy, you can also write a separate assembly file and link them together if you want to practice like that. Okay, so if there's no questions, then since I did the bulk of your print statement, I have a question about the quiz, the address of the third command line argument. Okay, let's go take a look at that. Let me not show you my password when I log in. So assignments, quiz 4, right? Quiz 4, or is it quiz 3? The address for the third command line argument. I think I know which one you're talking about. It is this one. Where is the address of the third command line argument stored in assembly? Okay. So remember how higher level languages work, right? So you have your main, and then you have your arg c, and then your arg v, right? These are the two arguments that are passed into your main function. Okay. Ouches. So in assembly, we have the equivalent, right? Remember that in assembly, our function call, our standard calling convention, says that the first argument passed goes into RDI, right? So this argument here is an RDI, and this argument here is an RSI, right? So remember in our example, I think we had a program 1, 2, 3, right? So this would be the first argument, the second, and the third. This would be the fourth, right? So in our argv, right, this contains the items, and their strings, right? 2 and right. So all it's saying is where inside your RSI can you reference this this argument back, and that's all it is. And remember, the RSI is the address of arg. Okay, so hopefully that more or less answers your question. Okay, sounds good. Are there any other questions about the assignment or the quizzes, or any of the lecture topics we've gone over so far? I think when I go over the code early today, it might have been a little bit fast. I wanted to make sure that I could squeeze in everything into the lecture. And if you need help, you can always rewatch the video and slow it down and try to follow along what the steps are. But I try to provide as much documentation when I did do the code as practice. So hopefully that also helps. Okay, well, if there's no, let's see, for assignment 4, how do we separate the variables into 3, L, W, H? Kind of confused on what we should make, that we should make our own variables. Here. I'm not sure if it's that confusing. You might be overthinking it. So let's say have a list, right? I don't remember all the values, but 200, 300, PD, so on and so forth, right? So you can kind of think that every 3 values is the sides of a cube, right? Every 3 values are your sides of your, not your cube, but your prism, right? So if you were to loop in your array, right? So in your loop, first you maybe grab your address. So if you wanted to grab this item, right? This would be the equivalent of maybe moving the word. Oh, let's move EX D word LST. All right. The next item is LST plus 4 bytes. The next item is LST plus 8. Right. And so this is your first 3. Then the next time you loop back, maybe you need LST plus 12, LST plus 16, LST plus 20, and so on and so forth. So this is basically the first value stored in 0 to 3. Next value stored 4 to 7, 8 to 11. Next value stored 12 to 15, and so on and so forth. So I'm not going to give you verbatim all the code for the assignment, but this should more or less be how you might want to structure grabbing your 3 values. Okay, all right. Hopefully that helps. All right. Is there any other questions on the assignment before I let you guys go? If you're curious about converting things into ASCII or printing integers to strings, I mean, Google is a very good resource to learn more about that if you're interested. Just you can do a quick search, and then there are a lot of good articles and resources that go into more detail than maybe something I would go over for an example. So if you're curious, always feel free to expand your library by looking at other resources, or there might be a section in your textbook that also covers that. I'm not completely sure if I remember. Or you can ask around the Discord. If I see your message and it's not answered already, then I'll maybe chime in and kind of talk a little bit more about that. But hopefully, the assignment's not too bad. I didn't intend for you guys to need to convert to ASCII, but it is good practice, so I guess that works out too. And it's only like an extra 10, 12 lines of code, so shouldn't be too bad. All right, so if there's no other questions, then I'll go ahead and end the recording here. I'll stick around for a little bit, and then I'll reteach the lecture material in the next class. All right, so that said, have a good weekend, and I'll see you next week.